Dear friends and colleagues, I wish you all very welcome to this 1-hour webinar on modeling wastewater treatment resilience. My name is Ulf Jeppsson from Lund University in Sweden. I'm the chair of the specialist group on modeling and integrated assessment within IWA, the International Water Association. And before we start the actual webinar, I want to take this opportunity to say just a few words related to the work of the MIA specialist group, which is organizing this webinar. The MIA group is one of the most active specialist groups within IWA, and the one that is really focusing on modeling of all aspects of water and wastewater processes and everything related to that. It is a group that is open for everyone who's a member of the International Water Association, and we currently have some 1,900 members. One of the most important ways that we work is through what we call task groups. This is a small size group of experts focusing on a specific topic for a number of years, and then normally producing towards the end an IWA scientific and technical report. Currently, we have 5 active task groups under the MIA umbrella. You see them here listed to the left. Secondly, we are also active through working groups. And working groups is another concept, which is often a larger group of people promoting and investigating a more general topic. And thirdly, we also reach out via our 2 main recurrent international conferences, the WRR Mod and the Watermatics. And speaking of conferences, our next main event is the WRR Mod 2023 Modeling Seminar, which will take place in Stellenbosch in South Africa in January 2023. And it will be organized by Dr. David Ikumi and his colleagues. Then in the late summer of 2023, we have the Watermatics 2023 Modeling Symposium. And that one will take place in Quebec City in Canada and will be organized by Professor Peter van Rollegem and Dr. Elena Torfs. If no one hears about our activities, what the MIA specialist group is doing and what it achieves, then of course we hardly exist. Therefore, we also have a number of channels for you and others who want to learn more about our activities and be able to follow news and updates and so on. We have the MIA website on the official IWA Connect system for all IWA members. But if you're not a member, you can find almost the same amount of information at our open website, which is available for anybody to look into. We're also on LinkedIn and Twitter, and we produce a regular newsletter. And then finally, we have our own YouTube channel where we make webinars, for example, like this one, generally available. So I would just hope to see you all as members of the MIA specialist group. If you're not already, then please join as soon as possible. With that, I want to leave the floor to Dr. Luis Corominas from the ICRA Water Research Institute in Girona, Catalonia, Spain. He will give a short introduction to the topic of today, and I wish you all a very fruitful webinar.
Thank you, Ulf. So my name is Luis Corominas. I'm a researcher at the Catalonia Institute for Water Research, and I've been working on modeling, monitoring and control of wastewater treatment systems, and have been working on resilience too. I will just give you a brief introduction on resilience, just 3 slides, before the speakers go into their presentation. So it's kind of difficult to find the proper definition of resilience applied to the water sector, but probably one of the best definitions that we found in literature is the one that we have in that slide. That states that resilience is the capacity of a system to absorb disturbance and reorganize while undergoing change so as to retain essentially the same pre-disturbance process, form, identity, and feedbacks. So somehow in the figure that we shown in here, will represent time on the x-axis and a kind of a state variable that represents performance of our system, our water resource recovery facility. And when we have a stressor that starts, like there's an event that starts, then the system goes into like a loss of performance until the soon after the event finishes. Then the system recovers and goes back to the original condition. So this is just a summary and shows like two metrics, for instance, like the recovery time of my facility against the stressor or the event severity, depending on the loss of performance. Next slide, Ulf, please. So given that context, so if we have our urban water systems, and we have direct stressors, and somehow climate change, human behaviors change the composition and the quantity of wastewater being generated and transported to the water resource recovery facilities. So these changes are direct stressors. So the system needs to adapt, needs to be resilient against these changes to guarantee the performance and to go back to normality if the system goes in a different state. Furthermore, we have indirect stressors. So if there's a certain infrastructure deterioration or we have failure, so the performance of the system might be affected. So the system needs to have strategies, need to build up resilience against these all stresses. And for instance, control might be a manner of building resilience, or redundancy in equipment, redundancy in sensors. And all that context makes it difficult to make decisions, especially on the recovery of resources. And hence, like, proper frameworks are needed to make all these decisions and handle with those complex elements. Next slide, Ulf. So in this webinar, we'll cover 4 themes. So mainly we'll talk about the use of modeling practices to evaluate dynamic resilience, how to visually communicate. It's not easy. There are so many metrics. So how to easily communicate and inform the operational staff, how to move forward in this topic, in this field, and how to address the challenge of modeling decisions on optimal process streams for resource recovery. Next slide, Ulf. So so we have 3 presentations and 1 Q&A session moderated by Maria Molino Senante. And just before starting the first one, just to remind you that this session is being recorded, microphones and cameras have been disabled, normal chat function is disabled, but please be active in the Q&A questions so that we can respond them immediately or in the Q&A session there. Having all that said, I would like to introduce the first speaker. So the first speaker is Timothy Holloway, and he's actually the promoter, the instigator of this webinar. So thanks for putting all this together. And Timothy Holloway is the senior scientific officer and chartered engineer working as part of an innovation hub collaboration between the University of Portsmouth and Southern Water in the UK. He's currently undertaking research on the dynamic resilience of wastewater treatment processes. So Timothy, the floor is yours.
Okay, thank you very much, Lewis, for that really great introduction. Today I'm going to be talking about coupling conventional modelling with resilience theory for improved operational decision making. As Lewis alluded to earlier, it's quite challenging sometimes to explain these very complex parameters to operational workforces. So in terms of the agenda for today, I'm going to start off with an introduction, then move on to the conceptual basis for dynamic resilience, then show you some state-based simulations we've done around Monte Carlo, and then move on to data-driven modelling around resilience using actual instrument data from 10 years of a wastewater treatment plant, and then give you some conclusions based on that. So from the introduction, I probably don't need to tell a lot of you this. Obviously, our population is increasing, albeit at a lesser rate. one thing I find very interesting is that actually by the end of the century, we will be 1.4 times the planet carrying capacity, which is quite worrying. And as a small island, the UK is very it could be quite challenging there. Also, depending on our path, we're likely to exceed the 2 degrees above pre-industrial levels. Rainfall intensity is also changing. So we're certainly seeing that in the data, is that the intensity of rainfall is increasing. So that for instance, has issues with CSOs and storm tank overflows. So in terms of the impact on wastewater production, well, I think given COVID-19, we've seen a lot of transient populations. So we've seen that changing quite a bit. So for example, in the West Country, where people have moved out of the cities, a lot of the plants are now becoming overwhelmed with wastewaters. We're also seeing quite significant dilution. So when we see these high intensity events, we're seeing quite significant dilution, but in between there, we're seeing extended dry periods. So we're seeing highly concentrated wastewater. So I suppose the challenge around that really is that these stresses are generating complex dynamic process stresses. So what we're proposing to do is to separate those two. So we look at them independently. So try to characterize the stressor, but also the process stresses that are happening within that particular technology. So where did we start? Well, we started looking at stress in particular, and we did a survey of wastewater professionals. So 200 participants, and hopefully there's some people on there, so I'll thank them now if they've already filled it in approximately a year ago. But it was fairly unanimous that from that, they thought that process stress was a variance from a benchmark condition or a standard operating condition. And stress measurement was viewed as most important, with 82% of the respondents saying they would use a tool for process stress measurement. So this really emphasizes that we need to separate these two things out to understand the stresses, so what's happening to the works, and also the process stresses associated with that. So it elaborates on previous resilience kind of theories. So our proposed extension, as I said before, is to separate these two things out so that we can look at them independently. And when you start to do that, and when you start to look at the time involved, you can start looking at kind of reaction times to events, and you can start categorizing and building knowledge of those historical events in more of a visual way so that you can communicate it to operators. Obviously, the flip side to that is that you can end up with periods in a diurnal profile where your process is actually relaxed, i.e. resilient. I say resilient, but that's mainly around physical processes where you can be resilient, whereas biological processes are always reacting to change. So they could go into a stressed position. So our proposed definition of dynamic resilience is that dynamic resilience is the temporal variation of stresses and process stresses in response to events outside of the original design intent. And I'm aware that a lot of the time when you've got historical assets like we do in the UK, that may not be available. So we've tried to come up with something that kind of gets around that as well. So in terms of the conceptual basis, and where I'll be focusing is the direct stresses, which generally come from the catchment. So they result from consumer behavioural changes, climate change, again, behavioural change in terms of, as we've seen with COVID-19, industrialisation and population growth. I'm not really going to focus on the indirect stresses in this presentation, but they're related to the asset, mechanical failures, poor maintenance, poor design, and operational funding. But both of these ultimately result in process stresses. So stresses are the cause and process stresses are the effect of those. So we started off looking at Monte Carlo simulations, and we very quickly got to a point where we realized that how many simulations we had to do to replicate reality. Although these do kind of represent what you would expect of a primary sedimentation tank, we then went down the route of looking at real data because it's important to know what's happening at that time. It allows you to react almost instantaneously. So we came up with this three-part process using mechanistic models. So we started off with the modeling, the ASM models based around heterotrophic bacteria. And we had two models. So the first model picks up on the standard operating condition or benchmark condition. And the master kind of oscillates around that slave. So that's how you compute your dynamic resilience. So that moves on to the second stage, which is that computation of dynamic resilience. So working out your variances and where you are from your standard operating conditions. And then from that, we go through a number of transformations to produce self-ordering windows. So almost like a fingerprint of what's happening in that process as a result of the changes that we're seeing in it. It wouldn't be right talking about data-driven models without talking about the challenge of using real data. And on the left-hand side there, you can see data over a 10-year period, looking at a diurnal profile. And as you can see, the range is fairly large, but also the data is fairly skewed. And also it's not really very normal or log normal. So it can be quite a challenge if you don't go through the right preparation to put through kind of off-the-shelf algorithms. I think as well, a lot of the time, the kind of temptation is just to simply take averages, and I kind of warn against that because of the way that the data is skewed, because you can end up with a skewed central tendency. But what can we learn from this? So if your data looks a bit like a smudge on the right-hand side, what do you do with that? So we came up with just a simple methodology to separate out three flow regimes. So we used simple clustering methods after data cleaning and validation just to separate three flows. And then the flow with the highest density of data points we used as the standard operating condition, as you can see there. And then you can see the oscillation. So the red line is the actual data that we're putting through it. So yeah, we are fairly accurately able to separate that out. So then we moved on, we started looking at time-based stresses and process stresses and how they react. And that led us to develop, well, to elaborate on some existing kind of parameters that are available. So we looked at process failure rates, but we also looked at that in the upper and lower tiers. And we also looked at the prominence of events, and actually the duration of the prominence is quite important when you're looking at instrumentation, because they either fail high or they fail low typically. So you can then discount certain ranges of data there. We also looked at the dominance, so the difference between the process stress and, the stressor and the process stress. And that gives you an idea of how dominant that particular event is on your process. So then we moved on to self-ordering windows, as I said before. These are kind of a picture of what's happening in your actual wastewater treatment process. So on the left, you've got a stressor, and as you would expect, the stressor, as the flow increases, has a more concentrated stress. Whereas the biological process reacts slightly different, because you've got a number of different rates which are interacting with this as the dilutions change within that process. An interesting thing to note on here is that although you have an ideal operating condition running through the plot, that will also, as the flows increase, affect your downstream processes. So you can pick that up by using a variety of these different plots here that we see here. And this is only reliant on the data that you can get. Obviously, it needs to be, we need a certain, I call it data richness, but it needs a range and depth to it to actually produce these plots. And the grey areas on the plots are areas where there wasn't sufficient data. But it's almost giving you like a fingerprint of how your process is reacting. So from that, in terms of operator communication, we can then take this to sort of a traffic light level, which gives operators early warning of events and can also allow you to apply interventions and also optimize against process stresses and the stresses that you're seeing. And once you've got a database of these, you can then react a lot quicker, as I said before. So this is kind of where we are now, and this is some of the current work we're doing, which is at fairly early stages at the moment. But we're looking at using the same methodology for a whole work. So going from primary sedimentation, activated sludge, and humus settlement. And these work in different scales. As I said before, we have primary sedimentation, which typically in this instance will work from -1 to 1. And then process stress and activated sludge, because it's biological, it's always under stress, so it's always reacting to change, albeit temperature, flow, load, those sorts of things. But what this really shows you is that the primary sedimentation and the humus settlement aren't really stressed, but actually when you look at the humus settlement in terms of the surface loading rates, you're starting to see stresses emerge. And the activated sludge in the higher flows and the higher loads, as you would expect, it's starting to show some stresses. So in terms of the conclusions, well, dynamic resilience of wastewater assets requires the separation of stresses from process stresses, so having those two parameters. It has also been possible to use actual instrument data to simulate and visualize the stresses and process stresses. And these dynamic stresses have been identified from real data and used to simulate the process stresses. So please, if you are interested in this research, there's a short survey there. It takes about 5 minutes, and feel free to do that. And I look forward to some good discussion.
Thank you, Timothy. It's been great presentations showing us like how to link the use of activated sludge models to communicate resilience. So this brings us to the second speaker today. So the second speaker is Guantao Fu. He's professor of water intelligence at the University of Exeter and a Turing Fellow at the Alan Turing Institute. So his research focuses on the development and application of new computer models and artificial intelligence technologies for resilient and sustainable water management. So Guantao, the floor is yours.
Okay, thank you very much. So in this talk, I would like to distinguish the two concepts, specified resilience and general resilience. Specified resilience is the resilience of system to one or more identified shocks. There are two challenges with this concept. We have found there are some trade-offs between specified resilience to different shocks. For example, you can increase resilience to one shock, but at the same time, you can reduce resilience to another shock. Specified resilience cannot deal with the unknowns, those so-called black swan event. General resilience is the resilience to all shocks, including those unknowns. It's very challenging to assess general resilience, and most assessment approaches are qualitative and property-based. So in this talk, I will try to provide a comprehensive and quantitative approach to general resilience assessment. This approach is based on system performance rather than system properties. I will also show how this approach is used to develop interventions to improve system resilience. In the Safe and Sure project, we develop an intervention framework, as you can see here. There are various threats, including known threats and unknown threats. These are imposed on our urban water systems, resulting in system failures. These failures can have an impact on system services and further lead to social, economic, and environmental consequences. To assess the general resilience, we adopt a middle-based approach, look at the impact state and failures. With two circled in the middle. The underlying assumption is that our engineers know better the water systems and can characterize all failures. So in this case, we don't need to know what threat caused the failure. All we need to know is to understand the impact and the consequences of failure. Using the middle-based approach, we can decompose general resilience into multiple formulations of specified resilience. So here's the example. As you can see, we have 3 failures, A, B, C. And we considering individual failures, we have 3 scenarios. If we consider two failures at the same time, we also have three scenarios, AB, AC, and BC. And the final scenario is all failures occur at the same time. So in total, we have 6 scenarios. For each scenario, we can assess, we can apply a stress and strain test to assess specified resilience. On the x-axis, we can increase the stress level from no failure to complete failure, represented using the range from 0 to 1. Y-axis represents the level of strain. Here is the level of service failure, normally represented using failure duration or failure magnitude. And each scenario, we can get one curve representing the system response when it's stretched. The area under each curve measures the specified resilience under that scenario. So the system is more resilient when the area is smaller. So with the interventions, we aim to reduce the area, that is to move the curves down. So the maximum area covered by all curves, the gray areas here, can represent the general resilience of the system to all failures. I will use one case study to demonstrate how the approach works. So this is an integrated urban wastewater system. It includes the sewer system, wastewater treatment plant, and the receiving river. The sewer system has 7 subcatchments, 4 storage tanks, and related pumps. Step 1 is to identify all potential failures. Here, we consider the increase in sewer flow inflows and pollution levels, and pump failures and air raising failures. In total, there are 14 failures considered. Step 2 is to identify all impacts. In our case study, the impact is measured using DO concentration and ionized ammonium concentration. We set an acceptable level according to some regulations. The DO should be greater than 4 milligrams per liter, otherwise the system fails. Ammonium should be lower than 0.068 milligrams per liter. For each indicator, we can calculate failure duration and magnitude. So we have 4 measures of strain. Step 3 is to generate failure combinations. With 14 failures, we have a total number of 16,383 failure combinations. You can see the number of combinations provided in the table when different number of failures are considered. For example, considering 10 failures at the same time, there are 1,001 combinations. Step 4 is to assess specified resilience for each failure combination. Considering one individual failure, we can run a model to assess the wastewater system performance. We got 14. We got a DO failure magnitude and the duration on the left-hand side, and ammonium failure magnitude and the duration on the right-hand side. Each curve represents one stress, that is one failure. So we have 14 curves for 14 individual failures. Similarly, we can assess specified resilience for 2 failure scenarios, and then 3 failure scenarios, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in total, there are 16,000 curves. Now we can see the overall picture of general resilience of this system. So there are a lot of information we can get from this graph. I just want to highlight one point. The system is more resilient in terms of ammonium. As you can see here, at the 40% stress level, the ammonium failure duration and the magnitude levels are much lower than DO failure levels. Now, I want to show how the result can be used for intervention development. The first step is to identify service measures which should be prioritized for improvement. If we compare the area for DO duration and ammonia duration, the two graphs at the bottom, DO level is less resilient than ammonium as it has a bigger area. From the top left figures, we can also see there are significant DO failures when there's no system stress. So that is when stress level is at 0. So improving DO failures should be prioritized. Here we can identify critical failure modes which contribute most to the service failures. The x-axis shows all the 14 failure modes. The y-axis shows the percentage of the failure appeared in the top 500 worst failure combinations. For DO magnitude, as you can see here, the failures A, I, and N are critical failures. Failure A is the increase in serial inflow. It appears in all 500 worst failure combinations. Aeration is also a key factor responsible for DO failures. So intervention should aim to reduce these priority failures. Now we can develop interventions to address priority service measures and failures identified in the first 2 steps. We consider 5 interventions: increase flow attenuation in catchment, increase maximum outflows from a storage tank by a factor of 2, double the capacity of the tank, increase aeration tank volume by 10%, and increase the capacity of storage tank by 50%. Now we can evaluate these interventions in terms of resilience. From this figure, we can see interventions 1, 4, 5 have little impact on resilience. The red curves in the radar plot represent the resilience without interventions, and the colored areas represent the resilience with interventions implemented. The curves and the colored areas are almost the same. However, intervention 3 has a negative impact on ammonium. It actually increases ammonium failure duration and failure magnitude. So this intervention should not be considered. Intervention 2 can significantly improve specified resilience in terms of all 4 measures considered. In particular, for DO failures magnitude, the top figures in the second column. So the interventions 2 should be the best options. So to summarize, we develop a middle state approach for general resilience assessment. It can consider the potential effects of unknowns on system performance without the need to determine all threats to the system. General resilience is decomposed into multiple components for assessment. This made possible for performance-based assessment, although the number of combinations could be very large, as you can see in our case studies. General resilience assessment can be used to identify priority service measures and priority failure mode. So this will help us to develop appropriate interventions. It may be easy to improve specified resilience, but our case study found it very challenging to improve general resilience.
Thank you, Guantao.
Yeah.
For this very nice.
I would like to just one thing. I would like to thank the entire Safe and Sure team for the work. Safe and Sure was led by my colleague, Professor David Butler at the University of Exeter. It was funded by EPRC and was completed a couple of years ago. So you can find more detailed information on the general resilience assessment approach in this paper. Although it's still in review, we hope it will come up very soon. Thank you very much.
Thank you, Guantao. Sorry for interrupting you in the last slide. So very nice, very comprehensive study and very complete. So with that presentation, now we move to our third speaker today. So it's on the resource recovery. and decision making. And I'll introduce you Seda Seku, who's a postdoc research fellow in applied operational research and a member of the Center for Operational Research and Logistics at the University of Portsmouth. So her research interests are combinatorial optimization, heuristics algorithms, multi-objective optimization, and their application in various real-life problems. So Seda, the floor is yours. And do not forget to start posting questions in the Q&A, please, that we can start responding and starting the debate there. Thank you.
Seda, you're muted.
Okay, is it okay now? Can everyone hear me?
Perfect, move on.
Okay. Today I will talk about modeling optimal process selection for the resource recovery from urban wastewater. And through this, I will show you the NERO's multi-criteria decision support tool as I am part of the NERO's project, and I was the research fellow responsible for the design and development of this tool. So through the talk, I would like to first describe the NERO's project and then give information about the conceptual framework of the decision support tool and the nonlinear programming model that we used in the development of the tool, and the small case study results, which also will take us to the algorithm that we will use in the final decision support tool. So as a start, NERO's project is an Interact 2Cs funded project, and it aims the adaptation of technology, increasing the adaptation of technologies for the recovering resources, such as water, nutrient, and energy. And the main goals for doing this, they were planning, the project is testing the demo technologies for their performance efficiency, providing a strategy for the decision makers to make a selection of technologies by thinking the economic, environmental, social, and technical impacts of it, and also creating a strategy for increasing the acceptance of these recovered resources by the community. In the project, we have 5 pilot partners that they vary based on the recovery that they are aiming to, resources that they are aiming to recover, and they were taking place in Belgium, France, Netherlands, and the Southern Water. In the meantime, we were the University of Portsmouth and the Hazret University of Applied Sciences are the knowledge partners. And the talk that I will give today, that it is the joint work of my colleagues in the University of Portsmouth, as well as Timothy Holloway, who is also here. And we had a great collaboration with the Hazret University with Hans and Maria. And we developed the decision support tool as the computerized decision support tools help us to overcome the challenges that we are having since we don't have systematic objectives and the systematic decision-making process. And in order to overcome these issues, we would like to propose a decision support tool for generating resource recovery treatment trains by overcoming the issues such as a vast number of available unit processes and variability in the wastewater influent. And also we would like to simultaneously we would like to also simultaneously recover the multiple sources, and these are also based on conflicting objectives, since we would like to recover based on sustainability targets. And the geographical and social context is even make it harder as the regulatory requirements are changing. And for these aims, the NERO's decision support tool is aiming to enable the decision makers to make informed choices based on these sustainable dimensions. And we would like to make the tool web-based so that it will be available for everyone's use that after the project ends as well. And in the conceptual framework of the tool, we have 4 main building blocks, and these are based on the user input. The information that is collected on the user input, it is combined in the information we had in the knowledge library, and then we use them in our model to make a final decision in terms of, actually not final decision, but generating treatment train based on all the multi-criteria that we have: economic, environmental, social, and technical. But at the same time, it will take into consideration the different target resources that the user has, and also the different raw influent characteristics that they are having. Not only the raw influent characteristics and the targeted resources are asked, also we would like to consider the country that they are having in and the pilot sites that they are aiming to as population equivalent. And all these information are informing the decision-making model. And through this, we are generating a treatment train that has all the information from the user, and also meeting the demand of the recovered resources. So for this one, and as first, we need to define the key performance indicators that we would like to take into consideration, and they were based on the economic, environmental, social, and technical aspects. And for each aspects, we come up with the sub-criteria, which are the key performance indicators, through our workshop and also our interviews with our pilot partners, as well as in the literature. In order to embed this information, these indicators, and make a connection with our modeling, we mathematically formulated those key performance indicators, and we would be able to then quantify these indicators. And the more detailed information about how we quantify it and the formulations are taking place in our paper. So by using the indicator, we could then know that what kind of information we need per each unit process, because the indicators are formulated in this way. And since we identified the key performance indicators and accordingly the required information per unit process, as well as the context-based information, we could then convert them as components of our model. So we suggest a weighted multi-objective mixed integer nonlinear programming model. In this model, we define the sets through our unit processes, and the parameters, they were including the feature of these unit processes, the targeted products, their features, what is their requirement in terms of the regulatory concerns, and also we also would like to know the product characteristics, and we also know the sustainability objective targets per criteria for our model. And our decision variable, this is the key thing that we are as an output of our model. This is the one that we were getting the answer of. And these were the unit process, whether it needs to be selected or not selected. So we had a list of unit processes, and then we would like to make selection from these unit processes, which one needs suits our demands and also our needs, as well as the flow that we have and the final product that we would like to reach. To be able to do that, we need to put some constraints, and for these constraints, we could then calculate the mass calculation. We could then calculate the mass of recovery products, and we could ensure the unit processes for recovery is in the treatment train. and we could then ensure the compatibility between the unit processes when we are listing them next to each other. And we could also comply with the regulations that are based on the country, based on the product, and based on the condition that we are in. And our objective function, in order to do that, as we are aiming to optimize our sustainability objectives, we would like to minimize the weighted sum of the normalized distance from these targeted objectives when we are doing the modeling. And for more information, again, for the formulations and the detailed model, you can find it in our joint paper. So by using this model, we use this model and we implement it in GAMS in the academic version of it, and we use the Baron solver to solve the model for different scenarios. And here the one that I'm showing is the large scale one with 100,000 meter cube per day with the flow of 100,000 meter cube per day, and different influent characteristics that we are taking into consideration in our model is taking place. In here, we gave equal weighting for the one that I'm showing in here, and we were aiming to recover energy, nitrogen, phosphorus, and drinking water. As a result, after we run the model for these conditions, we get the selection of the technologies that take place in these treatment train. And as you can see, there are grouping numbers in here, which group numbers that they were the main assumption in our model, that after we had the list of technologies, we need to group them based on their maximum COD and minimum COD concentration that they can take. And it helps us, after we select the technologies, how we can sequence them. So by this model, we could also take, I will just show a small example in here, that when we, for example, apply it for 2 different scenarios, we could see that how these scenarios getting different economic, environmental, social, and technical impacts. And you can see here the short version of the criteria that how equalize annual cost, potential income generation, noise, odor, and land requirements. For social, we had affordability, acceptability, and they were all in their scale, so that when we are making our final calculation, we need to normalize them. And when the multi-objective function that we are having in here, it is the one that we normalized values. And by this way, this is just a small example, but you can understand that how different impacts can be seen from different scenarios, and of course the selection of technologies are changing for these different scenarios. And we can also see what is the final concentration that we can get based on the data that we have. So although we have the nonlinear model and we could implement it in the GAMS solver, this is not really ideal for our final objective in the decision support tool, because we would like to make the tool available to everyone, and we would like to make it online. And we didn't want to have the barrier of barrier of having issues in terms of the software. That's why we would like, and we also would like to have more robust design rather than grouping the unit processes after each steps. We don't want to make these assumptions, and we would like to see that after each unit process is selected in the train, what is happening for the mass balances of each concentration level for the different type of compounds. And we also would like to see the detailed information in terms of costing when the flow is changing from the start towards the end. So that's why we would like to suggest our algorithm, customized algorithm. And in this algorithm, we are starting to have a huge set of solutions. And from this huge set of solutions, we are finding the candidate unit processes that can suit to the influent quality that we have in the beginning. And based on this concentration levels, after they after they are suitable with each other, we are selecting the unit process based on the weighted sum of all the criteria that we have based on the unit process characteristics. And after after every step, we implement the same idea until we are reaching the effluent, or if we are recovering water, reaching the product quality for this water, we are checking the final concentration is lower than the regulations. And after we generate our mainstream, we are going to the side streams generation if our targeted resources are not selected or cannot be recovered in the mainstream. We need to decide the side stream where we would like to add the unit process for our recovery, depending on which recovery we would like to do. And in order, after we select where we would like to do it, and it will based on the higher mass balances, and it can be combination of the higher mass balances of unit processes. And from this point, we are selecting the unit process at the moment based on the resource recovery percentage. And after mainstream and side stream generated, we are then calculating the treatment train-based evaluation for each criteria, such as acceptability, affordability, potential income generation, equivalent annual cost, and the other criteria. And after each criteria is calculated, evaluated, we are finding an overall weighted criteria calculation, and then we could then reach the best treatment train. So this is
Seda, sorry, you need to conclude.
Okay, and in the user interface, we are collecting for reaching this information in this way easily, and then we are showing the users that their resource recovery and discharge option based on what they entered. And as a conclusion, these narrow web-based DST can generate wastewater resource recovery trains, and we can provide the users the different economic, environmental, social, and technical impacts of them. And as a future improvements, we would like to integrate the life cycle analysis part, and we would like to fine-tune our search algorithm and do some more further validation of our findings with our partners. Thank you for listening. And I'm happy to have questions as we will have in the end.
Thank you very much for this very interesting presentation. Now we have some time for questions. I have here a question. I'm sorry, I'm going to present myself. I am Maria Molinos, and I am associate professor at the engineering school in the Catholic University of Chile. The first question is, what is the level of adoption of these technologies and methodologies across the water companies in the UK? And Alf says that wants to respond to answer this question. So Alf. Do you want to respond?
Sorry, did you ask me, Maria?
Yes, because
I was trying to fix the video here for another panelist. No, I just marked it because I think it would be good for the speakers to try to answer.
Okay. Sorry. So, Timothy, can you start with this question?
Yeah, sure. I'm just trying to get my video working, but yeah. So at the moment, we had quite a good reception. We just did the EWWM in Birmingham, and there's quite a bit of interest. So 2 water companies are interested at the moment. I can't say who they are for obvious reasons, and one of them I'm working with, also a consultancy, and again I can't say who they are, but yeah, there has been quite a lot of interest, and outside of that also developers of software, because I'm by no means a developer myself, so it needs to be taken to the next stage, which is actually developing the programming behind it. So yeah, in short, yes, there has been quite a bit of interest and interest in adopting it as a resilience measure.
Thank you. Wen-Tao, do you want to comment also this question?
Yes. I mean, for the general resilience assessment tools, so we applied these two different case studies to water distribution system and wastewater treatment systems. I think we have tools available online. You can find from our group website. It attracted a lot of interest. So we had, the talks with some, companies. But I think in terms of implementations and the skill, I think that is still a long way to go. I think this is still at the theoretical, study stage. They still need, more research in this area. How to assess the general resilience.
Thank you. There are also a couple of questions for Seda. The first one is it can Neurus decision support tool designs be purchased?
No, there is no need for purchasing. It will be available in the our lead partner website, and I think it will be also available in the project website. Unfortunately, I cannot give the link at the moment because there is something wrong and it doesn't work. But I can share the link after the project. After the seminar with the host, and maybe I can add in my presentation as well. But there is no need to purchasing, and it will be available online after the project, which is end of December this year.
Thank you. And this question, I assume that is also for you. Are there input parameters for capital expenditure and operational expenditure?
That's also another good question. These were we have CapEx and OpEx based on the flow function, which is taken from another decision support tool study called Poseidon, and I think they used some other literature also to develop these cost functions.
Okay, thank you. I don't know if there is an additional question from the attendants.
There was another one, I think, Maria. If
it was answered by Luis, but maybe you can answer also.
Yeah, I've compiled a response to it. It's in short, yes. I think this, what I've come up with, can be applied in the short and long term. Obviously, longer term data is better and improves the resilience and the definition that you see in the resilience maps themselves. But in short, yes, you can do it as you're starting up a unit as well.
Yeah. And finally, I have a question for the panelists. From your experience and from the work that you have done in the past, which are the main or the first action that the water managers should adopt to improve the resilience? Any volunteer?
Sorry, can you repeat that, Maria?
Yes, sorry, my phone was ringing. Which are the main or the first actions that the water managers should adopt in the wastewater treatment plants to improve the resilience?
Maybe I can respond roughly. So there are some approaches which would not need any model behind that, like increasing redundancy, implementing control. That's not a huge investment effort, let's say. But somehow, at some point, it's interesting to go towards a modeling the plant, modeling the system. And then this gives you much more flexibility to test strategies and evaluate the performance of the strategies to enhance resilience. But at some point, the model cannot handle and cannot describe the unknowns that Wantao was describing. So, and the models, the ASM models are meant to work under normal conditions. But when it goes really far away from the conditions, it is somehow it was designed, prepared, the model starts failing. So, I mean, there's the limit in the mechanistic models we have today to describe the effects of the unknowns. So, I don't know if this responds, and maybe the others can add.
Okay. Any
Okay.
additional comment?
Could I make a comment? I think we need to start with the policy. I think, in the UK, we have the Ofwat. Ofwat have a policy require all water companies, to provide resilient water supply. I think that's the starting point, right? I think for the water companies, the main concern, from my point of view, is the cost. What's the cost for providing resilience? Resilience is good, but they are concerned about the cost. I think if the Ofwat is required, what company to provide, resilience, so they need to start think about this.
Yeah, I'd just like to add to that, and I think you're right, Guangtao. And I think natural capital needs to come into it as well, as a potential cost, and quantifying the cost of natural capital and the destruction of that when you don't meet these permits is going to be quite important when considering resilience at the other end of a treatment works potentially. Because I guess a lot of wastewater managers will be focused mainly just on the failures that they have and reacting to those failures. And there's also other things around that need to be balanced as more of a holistic approach to resilience.
Thank you. I don't know if we have time for an additional
you can take
question. Sorry?
Take one more. Yeah.
Okay. So it was answered by Luis, but maybe you can explain for the audience, what is the difference between performance analysis and resilience for wastewater treatment plant?
Yeah, so resilience is broader. You need, several authors are proposing frameworks, and part of this framework includes performance, and you need to define performance metrics to fulfill the objectives for which you are studying resilience. So resilience is much broader. This is what I wanted to mention. And I see the question from Lina Pelia as well. Yeah, right. There has been efforts in providing frameworks terminology for resilience, but probably still the match with uncertainty is not there yet. I'm not sure if Wantao runs a lot of simulations, thousands. Maybe he has more knowledge about that.
The Timothy, Cedar, or Wantao, do you want to answer as well?
Yeah, I fully agree. I think the metrics, the concepts and the metrics are, I think, like key. We are still, nowhere near, to make a consensus, in this area. So we have different concepts in resilience. We just heard, the dynamic resilience. I talk about specific, and the general resilience, and the figures. I mean, the Louis showed at the beginning is the engineering resilience definition, right? So it go back to the same level, before the event. So we also talk about, the ecological resilience, which is, going to a different, regime. So we talk about the build back better. So in the post-COVID world, so it's not necessarily go back to the same level before the failure. I think that's there are lots of, the work required, what kind of metrics are required, to roll this out, to in practice.
Yeah, I think it's standardizing that, and then also communicating that in the right way as well, and communicating those metrics to the people who are perhaps operating the plant, because sometimes and I certainly find there's a disconnect between the technicians, the engineers, and the people who are operating the site. So it needs to be kind of transferable as an item. Yeah. Cool.
With that, maybe it is a good time to break up this little wonderful webinar. I would just first of all like to thank all the presenters and also the audience for this webinar. And we hope that you've enjoyed the show, and hopefully you also learned something, and hopefully maybe even got some ideas to bring back home. I would just also like to draw your attention to the next webinar that we are organizing within the Modeling and Integrated Assessment Specialist Group, and that is a webinar on anaerobic digestion modeling. It will most likely take place on November 22, and you will see announcements about it on our various information channels. And please also, as audiences to this type of webinars, if you have ideas of some future webinar, some topic that you would like to spread around to the modeling community, then feel free to contact me or Louis or any other on the management committee of MIA with your suggestion, and we will make our best to make it happen so that you can have a webinar on your specific topic. With that, I say thank you to all and wish you all the best for the rest of the day. Thank you.